All right, in this video, we're going to look at concavity and points of inflection for this problem we were previously looking at. So for my second derivative, I'm going to get a -2 times a -1/3 x to the -4/3. Okay, so I'm going to get a +2/3, and then I'm going to have, so x to the -4/3 is the same thing as the cube root of x to the 4th. Or the cube root of x to the 4th. You could write it either way. It doesn't really matter. Okay, so here I have a fraction. When I have a fraction, I set the top equal to 0 and the bottom equal to 0. So from the bottom equaling to 0, sometimes people get freaked out when the denominator has so much stuff. You're basically just peeling it all off. So I divide by 3. I'd take the 4th root, and then I'd cube. So we did all that work to get x is 0. Okay, so x is 0 is my one and only possible point of inflection. So we have to still do a chart to see if it is an inflection point. So when I do my chart, and I'm looking at 0, okay, so this is the version I'm going to plug into. So I'm going to go f double prime of, we'll just do -1. So when I plug in a -1, a -1 cube, the cube root of -1 is -1, but to the 4th power it's positive. Times a +2/3, this is positive. Okay, let's do it over here. F double prime of 1. If I plug in 1 in, the cube root of 1 is 1. 1 to the 4th is 1 times 2/3. I'm still positive. So it turns out that this is not an inflection point. It's always concave up. In fact, we already know what this is, right? Isn't 0 a local max? We saw that in the previous video. So what's going on here is that this function is always concave up. But I'm actually going to write it in the intervals just because what's going to happen is that it's like it goes concave up and then goes concave up again. So I'm going to go ahead and put that 0 there kind of like as a pause of where it's sort of, the graph is switching. It's not switching concavity, but it's just changing. Okay, so what I'm going to do is go ahead and pause this video for just a second, and we're going to put our picture all together. All right, I'm ready to graph this. So I went ahead and put my observations from the first video of increasing and decreasing, and then my local max and local min, and then my concavity was always up, but it's sort of, I don't want to say switching, but it's doing something strange, we'll say, at 0, 0. Because it wasn't an inflection point, yet we've got the sort of pause in the action. Okay. So we're going to start off first by plotting those 2 points, which are 0, 0 and 8, -4. So over here, I'm going to plot 0, 0 and 8, -4. Okay. Now, what's happening is that this is going to go increasing. And usually when we draw a max, right, we go up and then down and then up. Right? Isn't that what we usually do when we connect the dots? Okay, well, the good news is that this is increasing, this is decreasing, this is increasing. However, I've got it concave down and concave up. And according to this, the whole thing is supposed to be concave up. So what is actually going on here is that it's like that. And this is going to bend kind of upward like that. So it's like almost like kind of like a swag of curtains. So I'm going like this and this. So this is like a pointy cusp kind of action happening. So that's why it's got this strange concavity happening that's not typical for polynomials. So there's the graph of number 38. And of course, we could verify everything by going to Desmos and making sure that we're getting the same picture. But I do need to see your calculus. The calculus needs to be there. All right, good luck. That was problem 38.